Good day, folks. This is tutorial number 26 in the playlist that's called Dynamic Scenario Animation and Simulation in 3D Experiences platform. This particular tutorial, I will be actually modeling a rope, okay? And keep in mind that a rope is not a spring and it cannot sustain compression, okay? Now, there is no actual entity that is called a rope in the 3D experiences uh, 3D experiences interface. There is something called cable, and that was done in tutorial 25, but that's completely different. That's not really a physical cable. It's just a constraint so that when one thing moves, the other thing moves with it or according to some ratios. So that is not the same thing. So let me explain to you what I have in mind. As an example that I'll do later on for you, we have a support like that, and there is a mast that is attached through a cable to the support on the top. That's kind of uh, through my own writing or drawing, is that red piece that you see there. That really is intended to represent a rope. Now, when we model this thing later on, uh, that's going to look like that or like this, but keep in mind that the way I'm going to model this is through a spring that does not actually sustain any compression, which kind of behaves like a rope. Uh, but because of the size of these things that I'm making, what you see here, this big blob is actually a spring. You can see the coil, but it's so big that it looks weird. But anyway, it could be any one of these, okay, depending on the sizes that we pick. Now, here is an example of a cable, steel cable, for example. Notice that something like that can take tension. It has a stiffness in tension, but it cannot sustain any compression. Now, I'm going to assume that later on the problem that I do, the reference length of the spring is 50. What that means is that if the distance between two supporting points is less than 50, it's as if it's being compressed. But if it's bigger than 50 millimeter, that means it's going into tension, and as soon as it goes into tension, the stiffness kicks in. So here is the excuse me, the actual values that I'm going to be using. There is the mass of the block, 100 kilogram. I call it block, but it's really a cylinder here. And the cable stiffness is given to be this number. Now, remember, what I can use is some elementary formulas from strength of material. For example, if you have a rope or a bar under tension, the stiffness of it is kind of AE over L, area cross section, E Young's modulus over L, the length. But anyway, I'm saying that suppose that this is the stiffness of that cable in tension. So what we're going to do is to model this problem as a fixed part, of course. That's the that support that the thing is hanging from. There's a spring, and that's pretty much it. Now, I've done this problem with also insisting that that block moves as a prismatic joint, which is okay. You're not going to gain anything, at least in this problem, simple problem, by creating a prismatic prismatic joint which dictates the motion of that block. So I'm going to use the spring. That's pretty much it. Now, notice that when I try to input the properties of the string, I use the option extension only, and this is the stiffness that I was talking about, okay? This is Newton per meter. The other way of writing is like that. And of course, the gravity is acting, 9.81 downward. And later on, I'm going to plot this force in the spring, which means I'll be using joint force probe, okay, for the block. Now, initially, I'll be using symplectic Euler as the method to do this thing. And later on, I'm going to come and do it with the other solver integrator, DASSL. We'll do that later on. Now, Oh, this was intended to be symplectic Euler. Okay, so what we do is if you look at the deflection or you attach a probe to the, for example, the point at the top of the cylinder and monitor its motion, is going to be oscillatory, obviously, if there is no damping involved, and there is none here. And if you plot the force, notice that when it's under free fall, and we'll come to that in a minute, the acceleration is, the force is zero, okay? The force is zero. And then when it goes, the spring, essentially the cable becomes active, think about it like that. You're going to have a basically mass spring system, and it's going to be a sinus. So this is a sine, 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 and these are of course zero forces. Now, let me show you what happens. Initially, of course, this is the setup. The block is up there, and because the reference length of the spring is 50 millimeter, in other words, the distance between the top of the distance between the top of the cylinder and the bottom of the of that wall, that the 2 points there, if that is bigger than 50, it means the spring is in tension, and therefore cable acts as a spring. So what happens is that after, you'll see that after 0.101 second, this block reaches the free fall condition. Free fall condition ends here, and then spring becomes active, or cable becomes active, acts as a spring, and then it's going to compress it, not compress it, extend by another 8.371 millimeter. So basically, if you take this thing and multiply it by 2, you get the period of that oscillation, because this is half of the thing, and then it's going to go up again. It's going to go up again, reaches the place where the spring reference length becomes less than 50 or equal to 50. And then after that, there is no cable, does not resist any opposition, okay? Does not have any opposition. And then from here all the way to the top, it's just a projectile motion without any condition except for gravity acting. So you can see that after 0.228 seconds, it reaches the top again. So the period of this oscillation from here all the way down up is 0.228. Now, let's actually see whether we can get some theoretical results to confirm these things. On the very top, velocity was 0. This is the free fall. This is where the free fall condition is. So this is 50 millimeter. Free fall ends here. And from first year physics, we know that the velocity when it reaches there on the free fall is the square root of 2gh, and you plug in these values. H is the height here, 50 millimeter. You're going to get 0.99 meter per second. Okay. Remember, H is 50 millimeters. You have to convert it to meters, etc. So 0.99 meter per second. Now, from here to here, it goes into a mass spring system, basically, and reaches the very bottom, which is V equal to 0 again. It stops, okay? Now, from, again, elementary formulas, you have the time that it takes from here to here, 0.101. You'll see that it matches that. And then the period here, if you wonder where it's coming from, or the time here, we can think about the mass spring system. And if mass spring system under oscillation, it has a frequency of square root of k over m, and you can find its period, and you take 1/4 of that, you get this. Remember 2 pi over omega? Omega being the square root of k over m? You take 1/4 of that, you get this number. That's what I was referring to. That's where it's coming from. Now, how did we get that 0.8371? How did I get this amplitude? There are different ways of doing it. You can get it, for example, saying that over here we had the kinetic energy, and over here we have no kinetic energy. The two have to be equal. Compression of the spring gives you that much energy stored in the spring. This is kinetic energy. You solve for delta, you're going to get 8.371 millimeter, okay? And if you multiply it by k, you're going to get this. By the way, the maximum force, this number, I could have got it also by taking the amplitude of the oscillation the amplitude of the oscillation and multiplying it by or dividing it by omega, sorry, multiplying it by omega squared. That gives you the acceleration, and then we multiply by m, you get the force. But anyway, this is fine. There's nothing wrong with this. So these are the dimensions that I'm going to be using, although they're totally irrelevant, but I want to stick to this because I'm going to make the whole model. And the blocks mass, I'm going to declare it to be 100 kilogram later on. And the pin support, this L shape, inverted L shape, does not participate in the calculation, therefore it doesn't matter what it is. I assume that this was made out of steel, and then this is based on these dimensions. That's the value. That's the mass of this thing. But it doesn't participate in the calculation. Now, if I use the DASSL integrator, it gives you the same behavior, except that notice that there's some numerical damping involved here. You can see that. This is supposed to be a perfect curve. Part of it is parabola, the other part is sine curve, etc. But anyway, if you use this integrator, there's some damping involved, so we're not going to do that. Okay, so let's go ahead and make it. Right away, I'm going to save this thing. The first part that I'm going to insert is going to be the pinned wall. So right click, insert, 3D part, and I'm going to call it pinned support. Just give it a minute. Okay, right click properties. I call this thing pinned support. All right, let's go make it. Based on those dimensions that I showed you on this on the slide, which I'm not going to bring up anymore because these are not very critical. But I'll try to stick to those dimensions. So let's see now. We got something like that. We'll clean it up. My dimensions are actually in millimeters, so that minimize my work. Okay, let's do some dimensions here. First of all, I want this thing to be, what is that, a 5. Okay, and also this thing to be 5. All right, I want this inside to be 100, so this edge to be 100 millimeter. Okay, and I want that thing to be 40. All right, so we got it. So exit, and then I pad it symmetrically by 2 millimeters in each direction. 2 millimeters in each direction. So basically here what we get is our support, pin support. Now, while I'm at it, I'm going to create a point exactly at the centroid of this, because this is where the connection of the block is going to be. Now, how do we do this thing? We go to Essential, there is a point here, and different ways of making a point. I'm going to make it center of gravity. That means the centroid of that piece right there. You can see that is created right there. Okay, so this one is on the wall pin support, and then later on I'm going to have one for the cylinder. Okay, now that's pretty much it. Oh, but while we're here, why don't we create a plane, a plane that's 50 millimeters away from that? Okay, so we're going to create a plane, and offset from a plane, and this is my plane, and the value of the offset is 50. Okay, good. So what I have done here, I have created this plane, all right. Now we are done with this piece, so we go all the way to the top and insert our second piece, which is the cylinder or the block. Right click, insert, 3D part. I'm going to call it block, block properties, block, and block. All right, it takes care of that, and we're going to make it now. Double click on this. So what I will do is on that face, I will sketch a circle of the radius of it doesn't matter because essentially later on we're going to impose uh, the weight ourselves. So let me make it something like this. All right, and then make sure that it is the center is at that location. So this point, control that, either you make a dimension coincident or you do it a different way. Control Z, sorry, made a mistake here. Let's try it again. So dimension, how about doing dimension between this point and that point? Right click coincident, there we are. And that size doesn't matter, it may be a little bit bigger than what I have here, but that's okay. Exit. And then pad it by 10 millimeters. The other direction, make it 10 millimeter. Good. Now, what I will do is I will actually create a point. Notice that there's a point here, but that point belongs to the pin support. I want to make one which is at in the block. So for example, I can say I'm in the block right now, pin, point. For example, center of the circle, select that circle, and then say okay. So basically I have 2 points here. First point is on the wall or on the pin support, and the other one is on the cylinder. That's how we're going to define our spring later on. If it makes you feel better, you can also separate those 2 points, but I'll leave it the way it is. Okay. Good. Now we are pretty much done here. So let's go ahead and put some assembly constraints there. By the way, let me save this thing. Yeah. All right. So I go to, I'm in the assembly design, I believe. Is it? I'm in the assembly, yes. So let's go to geometrical connection, fix, and we're going to fix the pin support right there. That's fixed. You can see that right there. And then we are pretty much done here. There's nothing else to do. So we're going to switch workbenches and go to mechanical systems design, where we're going to define our spring and the masses and things like that. You click on it, mechanical system design. Why don't we, first of all, give masses here. So you scroll all the way to the right at the bottom, weight definition, you click on it. Everything is going to be red because we haven't defined any properties yet. So let me select the pin support and click this hyperlink to compute the weight based on the geometry. And never mind, let's do it. Let's do the top one. Assign. Now what I'm going to do is I will assign properties of steel by checking this box. We have done this many times, except that I'm going to change that. Actually, I don't have to change it because that's just leave it the way it is, because the wall or the pin support does not even participate. Now, if you see this number a little bit different from what I have in the slides, that's because perhaps the dimension on the slide was a little bit different. Something looks a little bit different. That's fine. Okay, so that's okay. We close that, and then we're gonna go and select the block, and we go and declare a weight, give it properties of steel, and then we're going to change that to be what we want, which is 100 kilogram. 100 kilogram, and when you're done, you click on it, and we're good, because you can see that the pin support is this, doesn't matter because eventually it's going to stay put stationary, and block is 100 kilogram, that's what you want. Good. All right. Now the next thing to do is to define axial spring. You click on the axial spring, wait for it. We want the 2 points. So 1 point was on the wall. It's easier if I picked it from the tree. 1 point was on the pin support. It was this one, and the second point was on the cylinder. Remember, I created the center. This point. See that? This point. And the type is right. So you click on f of x. Okay, click on f of x first. The type of the spring you want it to be extension only, and the value I gave it to you as 1.4 1.4 e to the 6 a Newton per meter. I think that's going to get converted. Yeah, 1.6. Yeah, it's equivalent to that value. So it is linear, f of x, and then the extension only, and those 2 points are selected, and we see okay. We say okay. Good. Now let's create our mechanism. Mechanism representation created. You click on this mechanism manager. There is a fixed support and there is a spring. Okay. And then we say okay. Good. So we are pretty much done here. Now we're going to switch to uh, uh, mechanical systems experience. Just say okay. We already have a mechanism there. All right. Now, first thing I'm going to do is apply gravity. Here's the gravity. See that? Gravity excitation. You click on it, and this is that's this box right there. 9.81 meter per second squared. The gravity, gravity on Earth, standard value. And then we're going to create a probe because we want to plot some stuff. I'm going to create a probe, and for the probe, I selected the point on the block. So it's easier if I picked it from the tree, this point, okay? And yep, say okay. And finally, we're going to create our dynamic scenario. Click on dynamic scenario. First of all, gravity excitation included, probe included. For parameter, we're going to use first the symplectic Euler. And over here, my first run was 0.456 seconds, 0.456 seconds. So that's going to be 0.456 seconds. Is that right? Let's make sure. Yeah, and then I want the results time step to be 0.001, just so that it looks a little bit nicer. Now, when I do that, and if I say okay, it's going to come back and say, hey, this number must be less than that or equal to it. See that? When I say that, it says hey, this has to be less than or equal. So I'm going to put another 0 here. And that's pretty much it. Okay, so let's go ahead and run it. I'll put it like this so that you can see what's going on here. Good. So first of all, save. Oh yeah, one thing I forgot to do, that force excitation, no, not force excitation, the probe, I forgot to put the force probe here. Let me go and do that. I forgot to do this, joint force probe, right there. Let me show you what I'm talking about. This one, joint force probe, I forgot to do this. So before I run it, I click on it, and I select the spring. I guess you have to do it from up here. Yep, and then block. Give me the force on the block, and then say okay. Very good. Yeah, let's save everything, and then we're going to run it. Put the cursor there, right click, Put the cursor on scenario, right click and click on that guy, or you know what to do, you go all the way to the right, click on this here, compute, but I'll do it like this. Just give it some time. Oh, I must have inputted some wrong number somewhere. Let's go ahead and find out what's going on. Something must have been wrong. Let me check my spring values first of all. 1.4, yeah, that looks good. And that looks good, extension only. Oh my God, I forgot to put the reference length of the spring. So let me go back to my axial spring. Reference length 50 millimeter. Yes. Let me save and run. Bad mistake. Right click, save and run. Yes. So before we do anything else, please do not forget to specify the reference length. Click on this reference length tab, put 50 millimeter. Bad mistake. All right, so let's go and do some post-processing. You click on the view scenario results, deselect everything. Let's look at two things. First of all, the vertical displacement. This is it. Position, vertical displacement, right there. That's one way of looking at it. There we are. Okay. And this this is fine, but I let me do something else here. Let's look at the. You might say, well, why does it look different from this kind of a graph? Because this is not, it goes over several periods. This is maybe over. Oh, you know what? Actually, if you go further, this was over 4 seconds, but if you go further, you're going to get that same thing. It is the same stuff that I did, except that the duration is not a 0.4. It must be, let me see, it must be maybe, let's do maybe 1.5. Well, it takes longer, obviously. Okay, so let's go ahead and run it. This is exactly the same plot. We're going to get the same plot, except that this was over a longer period of time. Oh yeah, it says 1, right up to 1. Because I did over a shorter period of time, 0.4, it looked weird, it looked different. It wasn't wrong, it's just that because the horizontal axis was from 0 to 0.4 instead of 0 to 0.1, it looks different. But now it's going to be more resembling what I have in the slides. It just takes longer, that's all. Just give it a minute. And it really doesn't matter whether you do the distance or you do the plot. It really doesn't matter. Now, if you go here and say, okay, show me, all right, everything takes longer because there's more results to retrieve. Just give it a second. Okay, so deselect everything. And if you look at the Z, yeah, looks a lot better. This goes 1.5. The plot that I gave you was over 1 second. Now, notice that there is no damping here. The heights are all the same. Now, if you go and change this, double click on that, and change this thing to change the integrator to DASSL. I don't want it to go that far. So let me go 1 second. It's a little bit shorter. And same run, except that different integrator. The results are going to be similar, except that there is some damping. You'll notice that any one of these heights can be compared in terms of time or in terms of displacement against these things that I have. I'm not going to bother doing that because if you're interested, you can check these yourself as far as the deflection below the 50 millimeter thing is concerned, etc. All right, good. So let's go ahead and look at the Z displacement. Okay, so we deselect all Z displacement. You see that there is some kind of damping. You can see that the heights are getting smaller. All right, folks. So good luck. Well, this is one way of doing cable in this rigid body dynamics for 3D experience.